want to start?
Today we're happy to have Gaetan, Borot here to tell us about Planck, to tell us about a generalization of Mirzakhani's identity and geometric recursion.
So thank you, Young and Artan, who is not there, for the opportunity to talk. So what I want to explain today is a general mechanism to construct mapping class group invariants. In particular, some that may be useful in hyperbolic geometry or maybe in string theory and quantum field theory. And the way, so this is some joint work with Andersen and Orantin. And the way we found this was by trying to look for a geometric meaning for the topological recursion of Andersen and Orantin, which is some recursive structure that governs many problems in enumerative geometry of surfaces, like certain case of Gromov-Witten theory, counting surfaces, discretized surfaces, or computing volumes of the moduli space of curves. So the prototype of actually this construction, which we call the geometric recursion, is Mirzakhani identities. So I will start by reviewing that. So in all the talk, a surface will mean, sigma will mean a topological, compact, oriented bordered surface. And so here a relation is connected and has order characteristic smaller than -2. And the basic block in Mirzakhani identity is the set P sigma of homotopy classes of embeddings of pairs of pens in sigma. There's one more thing which I want to consider about my surface is that they will have one special boundary for each connected component. So there's one boundary which I represent to the left, which is, you can think of in, and the other which are out. A way to make this distinction is to say that my boundary will have orientation, which may disagree or agree with the orientation of the surface. So I can split the boundary of the surface into one boundary component here, d minus, and the rest, d plus. So I want to consider embeddings of pairs of pens such that the in boundary of P coincide with the in boundary of sigma. And in fact, so this is a pair of pens, and I will consider it with, so that's the in, but I also want an order on the two other boundaries. Okay, so this is a countable set, which I can decompose. So there's the first boundary of the pair of pen, which is correspond to the first boundary of the surface, for example, here. That would be the embedded P. But then there are two cases. Either these two boundaries, there's one which is in common with the boundary of the surface, or there's none which is in common with the boundary of the surface. So I make this distinction here. And this is saying that I would mean that D plus P intersected with D plus sigma would be this thing. So either it's empty or it's another boundary component. So now consider T sigma, which is a Teichmueller space of sigma. So one way to describe it is the set of hyperbolic metrics with geodesic boundary and this up to diffeomorphisms which preserve the orientation both of the surface and the boundaries. Such as the diffeomorphisms which are isotopic to the identity and which are actually identity on the boundary. So if I take the point here, that's a hyperbolic metric, I have a way to give a length to homotopy class of simple closed curves. And in fact, in each homotopy class, of simple closed curve, there exists a unique geodesic representative. Okay. So, in particular, if I take a homotopy class of a embedded pair of tens, there will be a canonical representative once I choose this sigma, which is a hyperbolic pair of tens with geodesic boundaries. And in particular, then if I cut along this geodesic, if I cut along here, I still get a hyperbolic surface here. Which I will denote sigma minus p. And finally, I will denote L sigma p, the ordered triple of hyperbolic length. Of the boundaries of sigma of p. So for me, that will always be the first boundary in a pair of tens. And then I told you I have an ordering. My convention is that when I'm in this situation where the surface has two boundaries in common with the pair of tens, that must always be the second one, which coincides with something like that called B. And then that will be the third one. So in that case, that will be the first length, second length, third length. In this case, first length, and here, and all these two. Good. So now I can start defining what Mirzakhani identity is. So perhaps I will erase this. So I will define two functions, Bm and Cm, which are functions of three lengths. So the first one is this. So this is a hyperbolic cosine. And the second one is here.
So does that say LU times all that cosh stuff?
Sorry?
Does that say LU times all that, or is that log? What is that before the cosh?
Before the code, it's a log.
Okay.
And the bracket ends here. So I'm just writing them to say that they exist and they're quite explicit, but the form doesn't matter much here. Okay. So the identity is saying the following thing. So consider any hyperbolic metric on the surface. You want to represent the constant function 1 as a certain series over all homotopy class of pair of pens. And the series is as follows. So I can write it like this. So I just sum the different tabs of homotopy class of pair of pens I have. In this case, I will put a B here, evaluated on the triple of length of the pair of pens. And in the remaining cases, I'm putting 1/2 of C. And this is equal to 1. So it's not completely obvious if you look at this that this sum converges. You can prove that by elementary means. But in fact, the proof of Mirzakhani doesn't need to prove convergence a priori, because you know it. In fact, what she does is taking the surface here, so when you have a hyperbolic metric, you also have a unit length way of parametrizing this boundary, and start to shoot geodesics orthogonally, and try to see what's happening with this geodesic. So either you can be in some pathological situation, but they're not very common. They have measure 0 for the starting point. So typically what you will get is something like that. In that case, this determines the homotopy class of pair of pen by looking at the free homotopy class of these curves. So the boundary is here, and this one. So if you look in the free homotopy class of those, you will find a hyperbolic pair of pens. So any geodesic like that, which is not pathological, gives you a homotopy class of pair of pens. Conversely, if you have a homotopy class of pair of pens, you can look which set of points on the boundary are so that when you shoot at the geodesic orthogonally to that, you will get exactly to that pair of pens. In that case, you can just partition this set, depending on which homotopy class of pair of pens you get. And these are the measures of the different components up to a set of measure 0 that doesn't matter. So that's more or less everything. So by measure theory, just know that this conversion is equal to 1. So the way she used this identity, we generalized the result of McShane, which was known for the torus one functor, is to obtain a recursion for the Weil-Petersson volumes of the moduli space. So define the mapping class group to be the orientation preserving diffeomorphisms, modulo the one which are isotopic to the identity. And among those, I can consider the ones which actually induce the identity on the boundary. So the moduli space of border-driven surfaces, M sigma, is the quotient of the Teichmueller space by this group. Since we have boundaries, in fact, this action is free and proper discontinuous, so this is a manifold. You can look at the sublocus of this manifold where you fix the boundary length, hyperbolic boundary length. So I denote that M sigma of L. So if sigma is just G with n boundaries, that has dimension 6G minus 6 plus 2n for any fixed L. And this carries volume form, actually it carries a symplectic form, which is called the Weil-Petersson volume form. And this is such that it gives M sigma L finite volumes. I will denote VGN L1 LM. So for low topology, you can actually explicitly compute what this volume form and try to integrate it in a fundamental domain. The Teichmueller space and get these volumes. For example, that's what Penner did in a few cases. And the corollary of this theorem on Mirzakhani is that now multiply this by the volume form and use the fact that the Weil-Petersson volume form behaves well when you cut using Fenton-Nielsen coordinates. What you obtain here is that you have to integrate that over the moduli space. And here in this sum, if you just take one term, you see that this sum reconstructs all the mapping class group translates. So integrating this big sum over the moduli space is the same as integrating only one term in each orbit, but over the Teichmueller space, modulo the stabilizer of the corresponding pair of pairs. And in this way, you're going to obtain a recursion for this. And the terms in the recursion will exactly be in correspondence with the finitely many orbits of diffeomorphism class of pairs of pairs. So you obtain that VGN L1 Ln is integral over all lengths of this B function. And that term was corresponding to an orbit where you lose one boundary because it's already there. So actually, you have to remember which one was common with the pair of pairs, so that's here. And then you have the C terms, where now you have two lengths on which to integrate. You integrate the function C, and here you have two types of orbits. Either you lose one handle and you gain one boundary. So that means when you remove the pair of pairs, you remain connected. Or you may disconnect the surface. In that case, you have to sum up the general of the components D and to split the set of components, maybe like this, L2 and N, in 2, and here you get VH1 1 plus J1L J1, VH2 1 plus J2, L prime J2. And this makes these volumes very computable. So more or less, this is a prototype of what I'm going to say. And I want to define what is the geometric recursion. Valued in continuous function over Teichmueller space. So the goal is to produce continuous function on Teichmueller space which are naturally attached to surfaces, which means they're compatible with isotopic class of Diffleo. In particular, that means which are mapping class group invariant. And if I have that, that means it will descend to continuous function on the modular space. And we are going to do that by induction, a bit remembering this structure, by induction on the order characteristic on the surface. So it will be a recursion, so we have some initial data. So initial data would be 3 elements A, B, C, which are in continuous function on the Teichmueller space of a pair of pent. So this is the TP is a space of hyperbolic metrics on a pair of pens. It's totally specified by the 3 lengths of the boundaries. So this is the same as a function of 3 positive variables. And I will also have a D, which is a continuous function for on Teichmueller space of a torus with 1 hole. And I want it to be invariant under the mapping class group of the torus with 1 hole. I will also assume that A, which is a function of 3 lengths, is symmetric under so the mapping class group of the pair of pent. In my case, I have the in boundary which is special, so that cannot be touched by the mapping class. The only thing what the mapping class group can do for a pair of pent is permute the 2 other boundaries. So I want A and C, but not B, to be invariant under that, which means that this has this symmetry. So I start from such data. And the definition I would like to make is the following. So first, I will reduce to the connected case. Because if I have a disconnected surface, so that's a continuous function on Teichmueller space of the Zhejian union, which is just the Cartesian product of the Teichmueller space. So it's a function of 2 hyperbolic metrics on sigma 1, sigma 2. I'm just going to take the point-wise product of the function of each metric. So now when I'm connected, the base cases which I want to consider will be Euler characteristic minus 1, which means pairs of pens and tori with 1 boundary. So I'm going to use this. So for a pair of pens, I'm going to take A. And for the torus with 1 boundary, I'm going to take D. And now, if I have an Euler characteristic which is smaller, I can start removing pair of pens. So what I want to define is omega sigma, which is going to be a sum of all homotopy class of pair of pens. So I have all these cases. And in this case, where the pair of pen has 2 boundaries common with the surface, I got a B. Which I glue to omega for the rest of the surface, which I already have by recursion. And that I just evaluate to the restriction of the metric on the rest of the surface. And I do the same for all the other homotopy class of pairs of pen, but now I do a C on the 2 boundaries of the pair of pen are inside the surface. So this is an infinite sum. If it was well defined in some sense, automatically that would be mapping class group invariant, because the mapping class group just permutes terms in this big sum. So I just have to find conditions on initial data so that these sums make sense. And this is what we do. So perhaps here. That we prove with Andersen and Orantin. At some point we also use a lemma which I got with Hugo Parlier. And says that if, so I write things like that. For any s and epsilon, there exists a constant, so m epsilon m prime s epsilon, such that a, so it's a function of three lengths, and I want that when these lengths are bounded away from 0, a is going to be bounded. I want a similar thing for D, which is a function on Teichmueller space of a torus with one boundary. So, of course, this Teichmueller space is not compact. One reason for non-compactness is that you can pinch cycles. So I just want to consider a set of metrics where the systole, which is the length, of the smallest curve, is bounded away from 0 by epsilon. So I don't pinch cycles. That should be smaller than m epsilon. And you want something on B and C. So if you want something like that to converge, the problem is that you can have very, very long curves on which you're cutting. So you want some decay on the length of curves you glue for B and C. So a decay faster than any polynomial is good enough. But since the boundary lengths here can be arbitrary, you have to say something about uniformity. So this is why I have this slightly complicated condition. So let's take this up. L1, L2, L bigger than epsilon of B, L1, L2, L. And here I'm going to define x plus, which is a maximum of x and 0. And I want this condition. So this condition means that if L is very large, but the boundary lengths are fixed, I'm going to decay faster than any power law. If L is very large, but the boundary lengths are also even much larger, I just want that this thing is bounded. And you want a similar thing for C. So these are my admissibility conditions for the initial data. And if they're satisfied, then this is recursively well defined in the sense that it converges absolutely on any compact of Teichmueller space, and in particular it's mapping class group invariant. So in the case of Mirzakhani, if you plug the function a, b, n, cm I gave you plus the function 1 here, it just interprets Mirzakhani formula as a recursion to get the constant function 1. So since this condition, they're very flexible, you may wonder what kind of other functions you can get from this. But to give you also an idea of the use of such a thing, because this formula is pretty hard to compute with, you have to do this infinite series. You also can prove an analog of what Mirzakhani did by integrating over the moduli space. So that's the first part of the theorem. And the second part is that if m and n prime are independent of epsilon, then this is integrable with respect to the Weil-Petersson volume form on the moduli space where you fix boundary lengths. So you can define V sigma, or let's say V omega Gn to be this integral for a surface of genus G with n boundaries. Again, this Weil-Petersson volume form. And automatically then, this satisfies the topological recursion. Which is the sum over finitely many terms, where the recursion kernels are just integral operators, where A, B, and C play the role of the integral kernels. So what we have is a general mechanism to produce functions on Teichmueller space, which are actually on the moduli space, and whose integrals satisfy this topological recursion. Another way to think of this is that this omega sigma, it satisfies some kind, is that the function that satisfies some non-gluing, non-local gluing conditions. Because if you think, imagine that you want to produce some mapping class group invariant function by gluing. So you can say I start with a surface and I cut somewhere. And if I know the function here, and the function here, and the function here, I can just try to glue. But that's only going to have, if that's gamma sigma 1 invariance and that is gamma sigma 2 invariant, the gluing is only going to have as group of invariants the stabilizer of this curve, of the homotopy class of this curve. The only way to restore mapping class group invariance is to sum always all homotopy class of curves on which you glue. And this is what this formula is doing. So it's very different than in T2FT, where you can cut a single thing and have some recursion. Here you have somehow physical series coupled to gravity, and that's the type of gluing procedure that you may imagine can occur. So the next question is, are there interesting elements in the image of this construction? So we have seen the function 1, and I'm going to show you another one.
But in particular, what's going to be interesting is if they have alternative descriptions.
Exactly. So if you have an independently defined function,
okay,
you may ask whether it satisfies this recursion.
Mm-hmm. Good.
Exactly.
This is kind of an absurd question, but could you rig it up so that you don't get mapping class group invariant things, but mapping class group covariant things to produce some kind of modular form behavior?
Yes, because then you just look at a certain equivariant bundle
Right.
of a Teichmueller space and look at sections of this. So mapping class group equivariant is the same up to a fiber product construction as mapping class group invariant.
Okay, great. And sorry, I don't know if you're going to come to this at the end, but are you going to tell me that the set of functions that satisfy these topological recursion rules, these gluing rules, are like something meaningful in terms of 2D gravity, some kind of Carl ring, or?
So what I was trying to argue, from the physical perspective, why would you consider these sums?
Uh-huh.
If you try to apply naively the gluing construction, cut the surface, and you want at the same time to restore the mapping class group invariant, you're led to consider sums of all homotopy classes.
Yeah, no, sorry, I agree with these words. I was hoping for like something precise in terms of some physical theory, and you tell me that this set of functions is something precise in terms of that.
Not yet.
Okay.
However, one thing that you can wonder if you can get conformal blocks this way.
Yes.
So I don't know the answer yet. But I can say that the space of continuous section of the continuous section of the vector bundle of conformal blocks, you can produce some stuff like that, equivariant continuous section of this bundle. But then you would have to say, if you really want to compute conformal blocks, first that they are real analytic in some way, second that they are a constant covariant for the KZ connection.
Right.
And that so far we don't have. somehow you produce too many things.
Yeah.
And only very specific sorts of initial data may lead to something physically meaningful. So now we'll give more examples, which we can think of as generalizations of Mirzakhani identity. So let me take a test function from r plus to r, which decays fast enough at infinity. For n-gas. And what I want to consider is also for a given sigma, the set of simple multicurves without multiplicities. So it's a long way to say that you have a surface with boundaries, and you will consider the set of the collection of simple closed curves, which can be discriminated, several of them, but I don't want that any of them is homotopic to one another, neither homotopic to the boundary. So the maximum number of components I can have is 3g minus 3 plus n, because then when I remove it, it cuts the thing into pairs of pens, and in a pair of pens we don't have any of such multicurve. So this is an example with two components, and so they have at most 3g minus 3 plus n components. Without multiplicity just means that I'm not going over several times. Good. So here's an independently defined function on Teichmueller space. Pick a hyperbolic metric and sum of all such multicurves with some parameter t, which remembers the number of components, and then you take the product of all components and you test the length, the hyperbolic length of this component with the function f. If f decays fast enough, that's going to be finite. Good. So the theorem is that you can obtain that by geometric recursion. So this is equal to omega sigma for initial data. So I already noted AF. And this is the same as AM. M was for the Mirzakhani initial data, the one that produced the function 1. In that case, I can even say that was the constant function 1. For B, so it's a function of two lengths of boundary and a length of a curve I'm going to glue on. So this is going to be the B of Mirzakhani plus T times F of L. And here it's a 1, but I can write this one as AM L1, L2, L. For C, we're going to take again the function of Mirzakhani and put some piece of B inside. L1, L2, L1, L prime. So C had to be symmetric in those two, so I have to restore the symmetry here. And there's also a piece of A. And finally D, where here I'm going to cheat, because anyway, D was the way that I defined my function for the torus with one boundary. So I'm just taking f of the torus with one boundary. So this initial data satisfy the possibility condition and produce exactly this function. So I will try to explain the proof, which is in fact very simple once you have the idea. So you want to find a recursion for this. And the good way to think of this is actually to say that here there's a 1, which is a constant function 1 on the Teichmueller space of the surface where you remove that multicurve. So I have a Jesuit representative in these homotopy classes. So when I get a hyperbolic surface as before, so I can do this. And then I use Mirzakhani identity as a partition of unity to express that as a sum of pairs of pens of sigma minus gamma. Once I'm here, since I know my sums are absolutely convergent, I can exchange the two sums. When I do this, so this curve is not allowed to cross the pair of pen that I have here. So when I do that, I will have the sum of all pairs of homotopicals of pairs of pens in sigma, and then the sum of all multicurves inside the rest of the surface. And when you collect all the weights of all these terms for a given pair of pens, you obtain these expressions. So you could play a slightly different game, which is pick any initial data which is admissible. Instead of putting the function 1 here, you can put your omega for some initial data of sigma minus gamma in this restriction. So that will be decorated by here. And applying the same idea, you obtain that omega for a twisted initial data, which is written here. You just replace the Mirzakhani function by your initial data. Okay. So that's always the generated family of new Mirzakhani identity. What you can do with it is, for example, take f to be a step function. So not quite because it's not continuous, but you can just smoothen it. And then you will count how many multicurves have lengths bounded by L. Or you can do some Laplace transform, or the same kind of way that appear in the Selbach zeta function. Except that here I really insist that it's simple multicurves. So you don't get the Selbach zeta function because in the Selbach zeta function you have to sum of all curves. It may be at the end that by a similar idea you can get to the Selbach zeta function, but at least you would have to consider surfaces with corners. Because what you would like to do is somehow to cut again, and then you would have many points on the boundary. So we hope that an open version of this will get to the Selbach zeta function. So there's several other examples. In fact, there's a general theorem or construction you can do that whenever you have something solved by the topological recursion, in the style of Andersen and Orantin, so for example, spectral curves or mirror curves of Calabi-L3 and so on, toric Calabi-L3, you can always, so you have a bunch of VG and L1 and M, which maybe are functions from n variables to n copies of a Frobenius algebra. You can always find a lift of the initial data to the initial data for the geometric recursion that will produce this after you integrate over the moduli space of curves. So you get some kind of densities on the Teichmueller space, or some decoration on the Teichmueller space over the boundaries. And it would be interesting to know what's the meaning of these densities. But you know that they integrate to known innovative invariants. So even so, what I showed was very much Teichmueller space related. In fact, you can run the geometric recursion in much more general settings. I want to sketch what you actually need to run this idea. What we start with, so where our construction will take value, is should be provided in the form of a functor from a category of surfaces to some other category. What seems to be vast enough for all possible applications you can think of would be, so actually what we consider is actually even more general than that, but locally convex complete Hausdorff topological vector spaces. So you need such a functor E. And before I was able to cut along the homotopy class of pair of pen because I was using hyperbolic measures. If you don't want to have something absolutely related to hyperbolic geometry, one way to do it is to have one marked point on each boundary component. So objects are the surfaces I told you, and morphisms will be isotopy class of D field that preserve the structure I have, or rotation I have on the boundaries. So what I would call target theory is the data of such a functor. And the goal is to produce elements here which are functorial assignments. So this functor means that we have such a vector space attached to each surface. And whenever you have an isotopy class of D field, you get a corresponding linear map, continuous linear map. In particular, these spaces get a representation of the mapping class group. So being functorial means compatible with all these transformations. In particular, that means that it's mapping class group invariant in this space. Good. In order to do that, you need a few more ingredients. So this plus functorial data of, so we'll make a list. First, you need a way to reduce from disconnected to connected, you need a way to make a union. So you need union maps, which go from this Cartesian product with this to E of the union. And I just want bilinear maps. I don't want to discuss question of tensor product at completion, I don't really need it. You also need gluing maps, maybe more important. When you have a pair of pens and a surface in which you excite a pair of pens, you then want to glue. Before it was a pointwise product, where you have to provide this way of gluing. In geometric situation, these maps are usually very natural ones. You have natural choices. What you have to work harder on is that I need to do infinite sums. So I need some kind of continuity. And that can be a bit more tricky. But in particular, I need a bit more than this. So here, these spaces, I need to realize them as projective limits of such things. And then I have a family of semi-norms, and it's all in the game. You have to provide it, and this needs to be continuous. And then you have to need a notion of length. So since I left the world of hyperbolic geometry, I have this sum of homotopicals of pairs of pens, I need a way to measure the complexity of this term, to have iteration. So generalized length will be something that take, so here I have some semi-norms. And I will need a function which to any homotopy class of simple closed curve, really not, so just not multi-curve, just one curve, associate some number, and it should have some properties which I'm not going to spell out, but which are the type is bounded away from 0 for any alpha. The number of curves such that this generalized length is smaller than some lambda grows polynomially with some constant depending only on the topology, etc. So this is really mimicking what we use of the property of the hyperbolic length to make this sub-conversion. So these data of E with this union map, gluing maps, this topological structure here, and this collection of generalized lengths, just finding some axioms, it's what I will call a target theory. And then you have a theorem, which I'm not going to write in detail, but which says that if E is the target theory, and A, B, C are some initial data, we satisfy some explicit and theoretical conditions. Then we can apply the same type of, we can make the same type of construction by summing of all homotopicals of pairs of pen using the green maps. And it's a well-defined functorial assignment. And even a bit more. So nice way to say what's a functorial assignment is that you have your category here, you have the functor E, but you also have a trivial functor that goes just to the base field. And a functorial assignment is a natural transformation here. And this geometric recursion is compatible with natural transformations that you may have here. You can compose. So what you can try to think applying this, so what kind of thing you can construct? So we have seen that we can choose E sigma to be continuous function on Teichmueller space. You can do the same with decorated Teichmueller space. You can do the same with some continuous sections of equivariant, looking in terms of equivariant unitary vector bundles over Teichmueller space. you can lose a bit of regularity by looking at radon measures. That also works. So these things I know that these provide well-defined target series. Now I'm writing down certain things that we haven't completely done yet, but which we contemplate, which is looking at differential forms and cohomology classes on Teichmueller space, or maybe decorated Teichmueller space, the one where you have a mark point on the boundary, because then it has more interesting cohomology. So in particular, if you were able to produce by this machine mapping class group invariant definitive forms, they would descend to the moduli space. And in particular, in this construction, you can maybe get interesting odd forms on the moduli, and so on. And in order to check whether that's that's non-trivial, you can always integrate over the moduli space. And then you get back to something you can compute with the topological recursion. So you can try to think of the same things on higher Teichmueller spaces. We don't consider PSL2R representation variety of surface groups.
Actually, do you expect to get odd forms? Because
Sorry?
do you expect to be able to get odd forms through this technique?
So far, the problem is not about odd or even. So first, moduli space has odd cohomology.
Yes.
You have to go a bit far to find them. Not like M111 does have. The problem that we have so far is more a topological problem of topology in infinite dimensions, which is, so there's a natural gluing map for forms. We have to prove that in some topology this thing is continuous with some normal estimates. And so far we have some problems. So there's a natural Weil-Petersson form metric on the Teichmueller space, so you can take the norm of the form with respect to that. And then you have something to evaluate pointwise this, and maybe d theta over L. And you have to understand how that behaves at the boundary of Teichmueller space.
Sure.
And for the moment, that's hard. We don't quite know how to do it.
Okay. Okay. Sorry. So here's another story, and I'm just not sure how it relates. I don't know the story for boundary very well, but just cohomology of MG, you've got these stabilization maps, or maybe I really mean with one boundary component.
Mm-hmm.
And then the stable cohomology of that is all like a Miller, Mumford, Morita type or whatever. There's no odd cohomology in that.
Yes.
So would that imply that anything you're able to construct by this, which I think is even stronger than being stable with respect to those boundary maps, you're not going to be able to see any odd forms?
So if you imagine that this topological problem is solved, then you can produce some stuff.
Yeah.
What you're going to say that these forms are going to produce, if they are odd, which nothing prevents stuff if the thing converge well to do, they're going to be zero in cohomology.
Uh-huh.
When you restrict to, say, fix the boundary length, or maybe even boundary length 0.
Uh-huh.
That will give you some new identity.
Oh, okay.
So if you can make that work, in both cases you win. Either you produce interesting stuff, or you produce new identities.
I see. Because you think you'd be able to find like the exact differential or something, or the antiderivative?
All we know the thing is exact, it's not...
No, but like, okay, so if you believe this claim that I just told you, which I'm not sure
Yeah.
is the same story, that stable cohomology is only even, then if you start with something odd, you know it's exact.
So if you have something exact, you can also try, because these gluing maps, the natural one is actually a chain map. You can try to produce the differential of which is the differential, or the form for which is the differential, directly also by geometric recursion.
Okay, cool. Gotcha.
It's lots of questions to explore if that works. Okay. So from a maybe more physical perspective, as I said, it would be very nice to see if you can get conformal blocks, which are known to satisfy some kind of sewing condition. But usually when you do this sewing in conformal field theory, it's some local thing. You degenerate the curve, and then locally near that divisor, you define your conformal blocks. Here it seems that if the B, and so this is not completely rigorous for the moment, I'm not totally sure, but the impression I had in my computations was that if you take A, B, C that decay very fast, like more than exponential and so on, then when you degenerate your curves just to pairs of pairs, maximal degeneration, just one term in the sum is going to give you the old Taylor expansion and near that divisor. And then the role of this formula is to actually say that what you do locally near maximal degeneration, you can extend it globally on the moduli space. So with that, I hope to be able at least to tackle some real elasticity condition, but it's still in progress. The last thing I can mention, which also is on a physical ground, so the idea I told you that when your theory is coupled to gravity, you may want to consider this kind of, if you want to do the gluing thing, you may have to consider this non-local gluing. I would like to have a path integral proof of that. Maybe for the densities on Teichmueller space you get from string theory. I don't quite know how it would work, but maybe something like that, a physical proof that this structure does appear would be nice. Thank you for your attention.
Have you looked at the Friedon-Schenker papers?
Which one?
Like they've got one in particular on like the analytic structure of conformal field theory.
Uh-huh.
So in particular, that second line that you said, or E of sigma you could take to be continuous sections of equivariant, whatever. This seems very similar to this statement of Friedon and Schenker that to define, if you have a 2D CFT, to be able to put it on a higher genus Riemann surface and evaluate its partition functions on genus G in general, it's equivalent to knowing the datum of the 3-point function and the 1-point function on the torus, or like a partition function on the torus and then also the 1-point function on the torus, this sort of thing. In other words, whatever understanding they have of cutting and sewing rules in conformal field theory seems equivalent to saying that they can reduce exactly to some set of initial data. Obviously, they don't care about the admissibility clauses and don't study the analytic condition well enough, but that seems almost equivalent.
Yeah, so some of that would be I guess what people consider in CFT is more the local aspects. Like near some degeneration, you could do this gluing and so on. So it would be interesting to see whether one can globalize that.
Well, so, I mean, when I say a partition function of a CFT at genus G, I really mean a function on all of moduli space, not just near some degeneration.
Okay.
So I think what Friedon-Schenker prove or prove at a physical level of rigor or whatever is essentially your statement. Just, with the additional hypothesis that it came from the CFT satisfying gluing rules, not that start with some initial data.
But, so, if I understand what you say, is they prove that this partition function is determined by the one on the torus and the pair of tangents.
Yeah,
Is that what you're saying? It doesn't mean that you have some way to compute it or a very indirect way.
Somehow this is what's handed down as folklore, but maybe this is just, like folklore doesn't need proof for even.
Yeah, even in physics, I would be very happy if these kind of sums naturally appeared in physics, but we haven't seen that.
Okay.
And my impression was that the only thing that are known is what happened with degenerate.
Yeah.
It's near some boundary of the model.
Yes. Okay, I see. But you're saying, like, I don't understand why you keep needing the coupling to gravity. Like just in.
Or just because you have something which has the diffeomorphism invariance.
Okay, sure.
Just that, not more.
Questions? There are no other questions left, and the speaker again.